Welcome, everyone. For today's prep, we're going to look at integration by parts, but for definite integrals. And really, it's just kind of keeping track of the notation here. How do we do this notationally? All right, so let's look at our notation. And the method we're going to use is kind of this second bit of notation here. So we have our definite integral that we're going to calculate. We know it's a definite integral because it has these little numbers, these little limits of integration here. This integral that we have to do is going to require integration by parts. So we kind of use our regular integration by parts formula here. And what we're going to do to kind of handle those limits of integration is we're just going to put brackets around the entire thing. And then the numbers there telling us that once we finish up with what's inside, we're going to evaluate. So we're going to go through the complete antiderivative process. We're going to go through the complete integration by parts. Do the whole thing, get the complete antiderivative, finish it off. So finishing off this remaining integral. And then once we're done getting the antiderivative, we're going to evaluate at the last step. The other option, perfectly fine to use this notation as well, is you still apply the integration by parts formula, but then you put a little evaluate sign on the first piece, which is already done. We don't have to do anything extra. So you can evaluate just that. And then the remaining integral that you still have to do, that can become a definite integral. So you'll end up with the same answer. Either way is perfectly fine. I tend to see fewer mistakes, though, if you just kind of finish off all of the integration and then evaluate at as your last step. So this is how we're going to be doing it. So let's try out example 1. We're going to integrate this function. And the function here is 2x plus 5 over e to the 3x. And it's a definite integral, so we're going to be integrating from -1 to +2. And as usual, when we have fractions like this, it can be helpful. Break the fraction apart and try to rewrite it so that it's not a fraction. And so in this case, we can get rid of the e to the 3x in the denominator by just using a negative exponent. So we can rewrite this as the integral from -1 to 2 of 2x plus 5 raised to the e, or times e raised to the -3x. So that negative there is what's getting rid of the division denominator there for us. And then we'll throw our dx at the end. All right, so now kind of we have more of a classic setup here for an integration by parts formula problem. So we have an algebraic function times an exponential. Kind of has that classic sign of a integration by parts. So to help us remember what to do, we can write down our acronym. So ILATE. And then we just look at the different parts of our function here. So we have a 2x plus 5 is one of the parts, and then e to the -3x is another part. So the 2x plus 5 is an algebraic function. It's a polynomial. And then the e to the -3x, well, that's an exponential. So the way we use this acronym is whatever's further to the left, that's what we pick for u. And whatever's further to the right, that's what we pick for dv. So that's our first step. Let's pick out u and dv. So u in this case is going to be our 2x plus 5, and then dv is going to be the exponential times dx. All right, so the next step is to calculate the two other pieces that we need. So we need du. So we're going to differentiate this. We get 2, and then we'll multiply by dx. And then we're going to integrate our dv here to get v. And this e to the -3x, this is a k-form. So the way we can kind of remember the k-form integration like this is the exponential function just stays as is, doesn't change. So it's going to stay e to the -3x. But then we take that constant k that's out in front of the x there, and we flip it. and we put it in front of the exponential. So we get a negative 1/3 in front. All right. So that's our first two steps. We got all the ingredients now. Now we want to actually apply the formula. So our integration by parts formula says if we multiply along the top, so the 2x plus 5 with that e to the negative 3x, that's the original function we're trying to integrate. So to apply the formula, we multiply down the diagonal, so u times v. So we're going to get 2x plus 5 e to the negative 3x. And I'm going to take this negative 1/3, put it in front of the 2x plus 5 there. It's helpful if you kind of rearrange the terms as you go. All right, so then we're going to subtract and integrate, and then I multiply those two terms along the bottom. So I'm going to take the negative 1/3 e to the negative 3x, and then multiply that with the 2. So while you're at it, it's helpful, simplify as you go. So we have a negative 1/3 times 2. Let's put those together. Make it a single constant, negative 2/3. And then we're going to have our e to the negative 3x. All right, so that's our integration by parts formula. That's step 3. All right, so how do we notationally deal with the fact that we're actually calculating a definite integral here? So, it's technically incorrect if we go from having a definite integral in one step to forgetting all about those limits of integration in the next step. So we got to make sure we include them from step to step. So we have two options, like I said. We could put a little vertical line here and then evaluate this piece. And then we could finish off the integration and do the definite integral over here. But I think it's a little bit easier, less mistakes this way, if we just take this whole thing, finish off all of the integration. So we still got to do this integral here. Let's wait until we start evaluating until we get that all finished. And we're just going to put our limits of integration here to indicate that we still have to evaluate. All right, so now let's finish off getting the antiderivative for what's in the brackets here. And what we got is a double negative. So let's simplify that double negative. Usually a good idea. Integration by parts produces a lot of negatives. So you want to simplify them as you go. So again, that first piece we're done with. And then I'll bring the 2/3 out in front as well. So this will become plus 2/3, and I'll move it all out in front of the integral sign here. So we have our e to the negative 3x then that we're going to integrate. And then we'll evaluate this whole thing from x equals -1 to x equals 2. All right, so we still got to do this integral. The nice thing with integration by parts is the integral that you still have to do, you've probably done something similar to that earlier on in the problem. And in this case, we did. We already integrated e to the negative 3x to get our v. So, it doesn't hurt. Go back up. Think about what you did back here, and you can kind of maybe reuse that or kind of use the same strategy. So in this case, e to the negative 3x, we know what its antiderivative is. So let's get it. And again, we got to just keep writing everything. We got our 2/3, and then the antiderivative of that exponential is -1/3 e to the negative 3x. All right, so now we're done with the integration. So pretty good. We're done with the integration. We're ready to evaluate, but it can be helpful to try and simplify your antiderivative down as much as you can before you plug in. Technically, we could just go right ahead now and evaluate, but I want to simplify this down just so I don't have so much to plug into. So what can we do? Well, if we look, we have a -1/3. We have a -1/3. Yeah, negative 1/3 here, negative 1/3 there. And then we also have an e to the negative 3x and an e to the negative 3x. So we have these these two pieces here that we're adding together, and both of them have a negative 1/3, and both of them have that exponential. So I always kind of like these exponential ones because normally there's kind of an exponential piece that we can factor out. So that's what I'm going to do. I'm going to factor that out, just to make this a little bit easier once we're ready to start evaluating. So I'm going to get the negative 1/3 e to the, don't need the parentheses, negative 1/3 e to the negative 3x. Let's factor that out. So what are we left with then? Well, we're left with 2x plus 5 and then plus 2/3. And then this is what we're going to evaluate from x equals negative 1 to x equals 2. And that's pretty good. We could go a little further and simplify the 5 plus 2/3. So what would we get? That would be 17/3. And let's plug in. So we got a lot of terms here to evaluate, so it helps when we're evaluating. Set up the parentheses, big set of parentheses for what you get when you plug the top number in. Set up a big set of parentheses for what you get when you plug the lower bound in. And then we're going to put a subtraction there in the middle. All right, so let's get that top number in. So we're going to plug 2 in wherever we see an x. So when we do this, we get negative 1/3 e to the negative 6, and then we get 4 plus 17/3. And then we play the same game. We take the negative 1, wherever we see an x, we're going to plug it in. So we're going to get negative 1/3 e to the positive 3 times negative 2 plus 17/3. And if we really wanted to, we could go through and simplify that down a little bit further, but that's pretty good. We're just going to leave it like that. All right, so that's the idea with doing definite integrals and integration by parts. So the main thing here is we're going to go through all the integration by parts process is exactly the same. And the way we're going to handle it is we're just going to save the evaluation until we're completely done with getting the antiderivative. And maybe if you want, you simplify the antiderivative down a little bit. And then we save the evaluation just for our very last step. All right, so we'll try another example like this in class. So we'll see you then. Bye-bye.